Okay, are you excited? Let's run the code. This is a process that may take a lot of time, sometimes hours. The speed depends on many factors, including the size of the dataset, the number of batches, the width and the depth of the algorithm, and the productivity of the computer you are using. On my computer with these hyperparameters, it took around 20 to 30 seconds to train the model. These are the results. As you can see, the training was completed in 8 epochs. This shows the validation loss started increasing and the early stopping mechanism was triggered. In other words, the model started overfitting. What about the losses? The training loss acted as usual. It was constantly decreasing. The validation loss was moving accordingly until the last epoch, when it increased. What we care about, though, is the algorithm's accuracy. After the first epoch, we achieved 93% accuracy. This is a good model already. It may be surprising that the model was so accurate even at the first epoch, but in fact there were several hundred batches that optimized the algorithm before the end of that epoch. That's the strength of batching. It is much faster and still accomplishes amazing results. What happened later is that the accuracy started improving, but in a declining manner. It jumped from 93% to 95%, and then gained less than 0.5% per epoch. Finally, we got a validation accuracy of around 97%. Let's see what happens if I change one of the hyperparameters. I'll fine-tune the number of hidden nodes, as it is one of the easiest to amend. Let's change the hidden layer size from 50 to 100 and run the code once more. The old parameters are forgotten due to the line of code we added earlier. Let's check the new results. We see that, with 100 nodes in each hidden layer, we have dramatically increased the accuracy of the model. Around the 4th epoch, we had reached the result from the last run. This time, the final validation accuracy got up to around 97.5%. Okay, cool. Does that mean we got an accuracy of 97.5%? If I'm asking, that's obviously a tricky question. No, it doesn't. That's the validation accuracy. We still must test the model on the test dataset. The final accuracy of the model comes from forward propagating through the test dataset, not the validation, as we may overfit. But didn't we already deal with overfitting? That's a fine point, as some of you could miss the difference between validation and test datasets. Let's clarify that. We train on the training dataset and then validate on the validation data. In this way, we make sure our parameters, the weights and biases, don't overfit. Once we train our first model, though, we fiddle with the hyperparameters. Normally, we won't change only the width of the hidden layers. We can adjust the depth, the learning rate, the batch size, the activation functions for each layer, and so on. Each time we make a change, we run the model once more and check if the validation accuracy improved. After 10 to 20 different combinations, we may reach a model with outstanding validation accuracy. So, we try to find the best hyperparameters. But these are not the best hyperparameters. These are the hyperparameters that fit the validation dataset best. Essentially, we are overfitting the hyperparameters. That's why we need the test. It is a dataset the model has truly never seen. We don't train the parameters on the validation dataset, but we adjust our model considering the results from the validation. With that in mind, validation is not the best instance for accuracy. Okay, let's test the model. We'll need to forward propagate and print out the accuracy, following the logic we used so far. This time, the data comes from the test dataset. Here's our test accuracy. It obviously differs from the validation one. It could be an improvement, or it could be worse. Doesn't matter. What's important is this is the final accuracy of our algorithm. Once we test, we are not allowed, at least conceptually, to change the model, considering the test accuracy. If we do that, we are overfitting the hyperparameters to the test, which defeats the purpose of the separation between validation and test datasets. Okay, that's about it. Our model has a final test accuracy around 97.5%. Take a moment to appreciate this result. Imagine someone came to you a month ago and told you, "Here are 70,000 photos of handwritten squiggly blotched crooked digits. Write an algorithm that recognizes which digit has been written." What would you think about that? Probably, you wouldn't know where to start. Now, with just a few lines of code, we've written an algorithm that gets 97 to 98 out of 100 digits right. This is remarkable accuracy, remembering the simple model we used. I'd like to conclude with the take of TensorFlow.org on the MNIST training. They show a model with an accuracy of 92% and ask, "Is that good?" Their answer is, not really. In fact, it's pretty bad. Our model was a bit more complicated than the one they show, and we achieved an accuracy of 97.5%. The question is, can you do better? Check the next lecture for instructions on how to do that for homework. Thanks for watching.